of the lecture, so those who cannot be for some reason will be able to listen to the lecture, or those who cannot would like to listen again would be able to do it. So okay, do you see a PowerPoint?
I don't do, at least.
Say again.
Yeah, I see something. I see a PowerPoint.
Okay, good. Okay, so hopefully you will see what I'm trying to lecture, and hopefully this smart board will be visible for you. So what is elasticity? We have this is the part of mechanics, like in the undergraduate study. Hopefully, all of you had the course in um, mechanics of solids. So this is a foundation for this course, mechanics of solids, and uh, we are going to describe the mathematics that are tools which we are going to use to solve 3D or 2D elasticity problems. There's not too many 3D problems that we can solve. We will solve only a few. We'll show how to do it. Mostly they are 2D problems that are useful in elasticity. They are so-called closed form solutions that we are going to discuss how to solve it. In the literature, we are discussing this, we are describing this as so-called boundary value problems. And we have two different formulations. One is so-called stress formulation, and the other is a deformation formulation. So depending on the constitutive equations and on the governing equations, we can set what kind of set we are going to use. Then we will go either from stress or from deformation with particular boundary condition, either stress boundary conditions or deformation boundary conditions. But before we do that, we need to um, uh, describe the preliminary information which is in the chapter 1 of the textbook that I uploaded for you, and hopefully you have in PDF. So after the lecture, you can read it and find all the things again over there. Now there's a lot of good textbooks for elasticity. The very traditional classical is Timoshenko and Ger elasticity book, but there are many others. However, they are out of print and can be bought on eBay perhaps. But they are very nice, and there's a lot of books which are all very good. This one I have picked because I have the electronic version, and this way I will not ask you to buy anything, to spend extra money, which these days are important to save. But hopefully you can learn both using notes that I'm going to provide and the textbook if something is not clear. So obviously, very important in terms of mathematics is the vector algebra. So we know, hopefully all of us, we know what is a vector. We usually indicate a vector by a letter. It could be capital letter or small letter. Usually, if we want to say that this is a vector, then we put it as a bold font, bold face, or sometimes we put arrowheads above the letter, or we underline the letter. But the meaning is that in three-dimensional Cartesian coordinate system, the vector has three components. So like here, you can see vector A has three components, AX, AY, and AZ. And if we want to find the magnitude, we put it as absolute value of this vector, or A without boldface, the regular face A. So if we want to find this absolute value, which is magnitude of vector A, we can do it by taking the squares of the components and taking square root, and we know that this way we'll have it obviously always positive value. Each of the components can be expressed using so-called unit vectors, I, J, and K, which are along the coordinates x, y, z respectively. And we can add and apply different mathematics for the vector algebra, like adding, subtracting, and we know that they are going to be done graphically, which means using parallelogram or a polygon method. However, we know that addition obeys associative law, which means we can add first or last or any two from the sequence of adding. We can also use a commutative law, which means we can switch A plus B with B plus A, and the result is exactly the same. Now, the other term of vector algebra is obviously the so-called dot product or scalar product. And one way of producing the results of the scalar product is multiplying the x components by each other plus y component by each other plus z component by each other. The scalar product is a scalar, which means a number. Vector is a quantity that has three components and direction and sense. A scalar is a just magnitude. So the scalar product can be calculated using magnitudes of A and B and cosine of the angle between them. This vector A could be also expressed using so-called direction cosines. And the alpha, beta, gamma we usually indicate as direction cosines, which is the angle between the vector itself or line of action of the vector and the coordinate x, y, z, which is starting from the line of action going through the origin of this Cartesian coordinate system, and the angle is between x and the line of action, y and line of action is beta, and z and line of action is gamma. The direction cosines also define the components of the unit vector along vector A. So in other words, the cosine alpha, cosine beta, cosine gamma are magnitudes of the unit vector, which is defining the direction or sense and line of action of the vector itself, vector A. So therefore, if this is unit vector, then magnitude of this of its components would be 1, and therefore cosine square alpha plus cosine square beta plus cosine square gamma must be 1. If you want to take square root of this, it will be also 1, right? Because 1 square or square root of 1 is also 1. So you can see here on the in the this corner here the direction cosines as they are defined, and sometimes we use alpha, beta, gamma. Sometimes theta x, theta y, theta z. It depends on the textbook or convenience, whichever we like. So the unit vector n in terms of direction cosines is shown here on the right upper corner, is cosine theta xi plus cosine theta yj, cosine theta zk. Of course, again, you can replace theta x by alpha, theta y by beta, theta z by gamma. And if you have this n vector, which is a vector, you can multiply the magnitude a times this unit vector, and then you have vector a as a vector. Now, the dot product is also possible to use with b plus c, and then it is the same as a dot b plus b a dot c, as you can see. So all this combination in mathematics work. Same thing as you have two brackets. In first is a plus b, the other c plus d, and you have dot products between them. So you can expand this and have a series of dot products the same way as we would do in the numbers. In addition to dot product, we also have so-called cross product. The result of cross product is a vector. And you can see, again, in the same drawing, if you have A cross B, the angle between them is theta, and A and B, if they are defining xy coordinate system, xy plane, then the result is vector perpendicular to xy plane, which is z, along z direction, and it has positive in this particular case because A is first and B is second. If B is first, A is second, then C would be opposite to invisible seed on this slide. So in other words, A cross C is not the same as B cross A. Okay, you cannot do the same with cross product as you could do with dot product. However, if you know the angle theta between them, you can find magnitude of C by taking A, B, and sine of the angle. And if you want to do it in as a vector, typically what we do, we create a determinant, and first row is ijk, which are the unit vectors of the Cartesian coordinate system that we use. Second row are components of the first vector. Last row is components of the second vector. And if you take determinant, normal way 3 by 3 of the 3 by 3 matrix, then you find the components of C in a component form, which is like A y b z minus a z b y times I, and so on, using each term grouped together by components I, j, and k. Then next to it is so-called cross triple product, which is also calculated using determinant. The only thing is that instead of ijk in the first row, you put A components, in the second row is B components, and in the last row is C components, and you take determinant. So obviously, this would be a number which is a scalar. So basically, the cross triple product is a scalar, is a magnitude, and it is a volume. It's equivalent to the volume of this shape that A, B, and C are edges of. And obviously, if all three are on the same plane, then the volume is 0, then the cross product is 0. So the summation of A plus B cross C plus D can also be expanded. And you can see as long as you keep the first term first and second, then you can distribute the product, the cross product, the same way as the dot product, and you will get the good results. Okay, so this much about the vector algebra. The other is the some definitions about the differentiations of functions. So scalar point function is the first one that we are going to discuss. And scalar point function is like a function that describes like mass density or temperature in space. So in other words, it is a magnitude prescribed to particular point in space xyz. And the derivative of that function is so-called total derivative, is calculated by using a so-called chain rule when you differentiate the first term with respect to x, the second term with respect to y, and third is with respect to z multiplied by dx, dy, dz respectively. So again, the outcome of this is a scalar. So differentiations of this is quite obvious. Now, if we consider that there is kind of the magnitude of direction given by ds, and that magnitude can be calculated as a vector, a square root of components dx, dy, dz, assuming that these are the components of small element, then we can find the direction cosines of this by cosine alpha, beta, and gamma. And we can express again the directional derivative to be the fds by replacing the basically dx ds by cosine alpha, dx dy by cosine beta, and dz ds over cosine gamma. And this is how we calculate so-called the directional derivative along the direction given by vector s. Now, why it is important? It is important because sometimes we are interested in that field of function f and find where is that direction of derivative is maximum. So this is the maximum value of the directional derivative, which is also known as a gradient. So gradient is giving us a maximum increase, you can say, of that function. Now, if you have a field and you have a point P, and you plot curves which is f of x, y, z equal to c1, and then another one which would be f of x, y, z is equal to c2, and so on. Those lines around point P are basically so-called level surfaces. And this is where you have iso curves of potential, which are giving the constant value of this scalar point function. Now, the gradient would be directional derivatives, which is basically perpendicular to those level surfaces. So this is what we are going to know, and the gradient obviously is given by a nabla form Okay, like here, gradient of f is derivative of df dx times I, y, and z. So the gradient, which is using this nabla operator, um, is producing from the scalar function a vector. Because why it has to be a vector? Because only in particular direction this derivative is maximum, right? We are asking ourselves in which direction this function is increasing the fastest way, the steepest way. You can imagine that those are like on the map, isochrones, the lines of the same elevation of the hill, and we want to go to the top of the hill. So this is where we reach the one that is fastest changing the orientation or the elevation of this particular hill. Nabla coefficient is also used for so-called biharmonic equation. This is Nabla square when it is not a vector anymore. This is second derivative, summation of the second derivatives of particular functions. So for example, if you apply this to the function f, which is this scalar, then we have the Laplace equation, which basically is giving so-called biharmonic formulas, and we are going to use it in elasticity for the so-called Airy stress function. Now, if you have any questions, so please ask, of course, anytime. You can, of course, ask later. Next time we'll have the opportunity when you digest today's lecture, you read the material, and then you may have questions. Now, today is mostly like references, is basically covering the material, the tools. So if I talk about particular biharmonic equation, we need to know what it is. So in addition to scalar field, we have so-called vector field. So here we assume that there is a function q that is like velocity of flowing fluid or displacement of a solid. You know, if you take about solid displacement, it deforms in particular direction. Okay, you may have direction x or y, and you extend the material, so the particles move along that direction when you have elongation, or maybe you have contraction effect as well. So this function again in space would be the vector in this case, because it will give us the so-called streamlines, which may have components u, v, and w. U, v, and w in elasticity would be displacements, and the path along those particles that move along for the displacements of particular particle will be called streamlines. It could be also used for fluid flow, but we will be always coming back to elasticity of a solid. So we can know that if u, v, and w are the displacement, that the along small deformation ds over q, where q is that velocity field is the same as dx over u, dy over v over dz over w, because they are all proportional. So this is like Thales theorem. The q function, the vector field, can be obtained using the gradient of the scalar function. So at that point, a scalar function f is called potential function of a vector field. So in other words, because it's giving us the velocity of deformation, which is the gradient in particular direction. Now, the other topic is the directional differentiation of a vector. And we can see how it can differentiate this graphically here. You can see the vector r, and dr is perpendicular to r, and r plus dr is longer than vector r. So in general, we can have the vector r to have components u times I, v times j, w times k. And if you differentiate the vector r, you can differentiate each of the components the same way. If it is time dependent, you can also differentiate with respect to time each component as well. So at that point, dr dt basically is defining the velocity, which is tangent to the change of position, as you can see on this curve. And if you differentiate this again, then of course you will get acceleration. And if this is the position vector r, and first derivative is velocity, which is the vector of field q, then second derivative will give us Newton's law, which is if you multiply this by moment, you will get the force, and therefore the second derivative of the r vector is acceleration. Okay. So we can also discuss the topic of differentiation of a scalar field. So if Q, capital Q, is a scalar point function in fluid, okay, so we can describe the behavior of this fluid from the Lagrangian point of view or Eulerian point of view. Lagrangian is when we look at the a particular change of behavior in time, and we would be we want this to be going together with the particle. Then this is so-called Eulerian description. So if we look at this from this equation here, this is the change of the density, let's say, of the particular element if we go together with this element. And this one is if you stick to the particular point and find what kind of density are flowing through this point. So this is Eulerian description, this is Lagrangian description, but all of them are linked together, so we can describe one from another. The other description is so-called for the vortexes, when you have the flow we will call curl, which is basically the using the cross product between Nabla operator and vector speed, vector field. I'm just going quickly because, again, this is just to point out those generic tools. In the fluid flow, Eulerian continuity equation is given by the equation here. This is the important that change of the density and so-called rho Q, which is the current density, will be altogether will give us 0, and this is the continuity of the flow of especially non non-compressive, uncompressive fluid. The exact differential is we know if we find the function m and n, for example, for two-dimensional, which has x and y, and we find that if the function f can be shown expressed in the form of m dx plus n dy, such that dm dy is equal to dn dx, or the difference of them is 0. This condition is necessary and sufficient for the differential to be exact. Similarly, in three-dimensional space, we can find 3 pairs of such conditions that we also define the derivative to be exact. Okay, so this is for the derivatives. Now I'm skipping a lot of theorems, which are Stokes, Gauss theorems. If you are free to read. Sometimes they are very useful. I would like to now to come back to the vector notation, but from the point of view of tensor algebra. So the dot product that we described already before, we know it is the summation of the components, products of the components, first, second, and third. And in this case, instead of x, y, z, we are going to use x1, x2, x3. So x1 is x, x2 is y, x3 is z. And by doing this, we will express this dot product as summation u alpha v alpha for alpha is 1, 2, 3. This is u dot v, correct? And instead of using the summation sign, we are going to drop it, and we are going to use u alpha v alpha for alpha is 1, 2, 3. So this is so-called summation convention. And any vector, therefore, can be described using the components. And maybe I'll do it here. And if this is x1, x2, the vector v, let's say vector v is like here. Vector v will have 2 components, right? v1, v2.
Hello, Professor.
Dr. Banyana,
Yes?
we don't see what you write on the board. I'm not sure if everybody else.
You don't see that?
No, we don't.
Yes, same here.
So the annotations are not showing?
It's just really bad quality.
So the smartboard is not showing the annotation?
No, it's not.
It's not.
Okay.
So when you move to the next slide, we'll see that you wrote something on the previous slide, but we don't see what you're writing.
Okay, so when I move to next slide, then you saw what I wrote?
I see like some red marks, but I can't read it.
I see. Okay, so let me. This is the problem with technology, correct? Let me see if I can do it different. Okay. Do you see hello?
Yes, sir. We can see.
Okay. Do you see that I erase hello?
Yes.
Okay. So maybe this application would be better. Let me try one more time, because now I share this screen instead of application, so that might be better. Let me see. Do you see now my notes here?
This works.
Yes.
It works?
We see
Okay.
the notes, yes.
Thank you.
So again, I wrote here U0, U dot V was summation U alpha V alpha, which is you can drop all the summation altogether and you have U alpha V alpha as described above. And if this is a vector V, then we can have V1, V2 as the components. And if I take another pen and make the different orientation, then I can describe the same vector using two different components, which is V1 prime, V2 prime, in X1 prime, X2 prime coordinate system. Now, what we are going to do is to define the components, and we will define those components as alpha and Aij. So those components would be like A11 would be cosine between x1 prime and x1 coordinate system, which is, this is cosine of this angle theta, okay? And A12 would be between x1 prime and x2 angle. So A12, do you see what I'm writing now?
Yes, sir.
It works, okay, good. So this is cosine between x1 prime comma x2, which is the same as cosine of pi over 2 minus theta, which is sine of theta. So in other words, I can describe those direction cosines as Aij and find the relationship later between the V and V prime, which would be the coordinate system. But in general, as you can see, those components like Aij produce the 3x3 tensor, which is symmetric tensor, but in general could be any tensor. And if this is any tensor, then we can always express this tensor by replacing the transversing this tensor from Aij to Aji, and by adding and subtracting, I can produce the symmetric and anti-symmetric components. So this is, for example, anti-symmetric component, and this would be symmetric component. And this is the method how you can, from any matrix or any tensor Aij, can express it in summation of symmetric and anti-symmetric components. Aha. Now I cannot switch. Let's see if I can do that. Okay. So now I'm coming back to the particular direction cosines, and I can tabulate this as I did it in the previous slide here. A11 was cosine between x1 prime and x1. So the prime can be put as in this particular table as a first column, and I put it in capital letters. So the prime this is capital, and the original was small letters. So AIB is the cosine between direction capital and small, or in other words, it is basically the dot product between prime coordinates and unprime coordinates. So let's show it here. This is unprime coordinates, so it would be E1 unit vectors, E2 and E3. And now I have prime coordinates, which is capital, so this would be E1 prime, E2 prime, and E3 prime. Okay? So if you know those coordinates, they are all defined with respect to the original global coordinate system, then you can calculate each component of this table by basically dot product between unit vectors, which are defining x and capital X, as long as you know that the first one is capital, the second one is original. Of course, from the dot product point of view, it doesn't matter, correct? But it is important to keep like this, because if this is A11, this is A12, which is different than A21. Okay, so in general, these are the direction cosines. So which means that components of the unit vector. So if they are components of the unit vector, then squares of those of each row and squares of each column must be 1. And if I'm looking for coordinate of particular vector in new coordinate system, then I can calculate it using this particular expression, which is capital X is A11 times X, A12 times X2, and A13 times X3 or Z. Okay, so if you see this table, which is easy to remember, this is the first index, which represents column, and second index that represents the first row, unprime coordinate system. Then you can reproduce the so-called transformation of the vectors coming from the unprime to prime coordinate system, or small letters to capital letters. Why do I stress so much? Because the problem number 3 of your homework is exactly giving that problem. Okay, so in problem number 3 of your homework, you have that E1 is 1 over square root of 2, comma 1 square root of 2, comma 0, and E2 is 0, 0, 1, and E3 as a vector, because each is a vector, correct? So this is a vector. 1 over square root of 2 minus 1 over square root of 2 minus 1, and 0. Okay, and the other term, E1 prime, would be 1, 0, 0, E1, E2 prime as a vector is 0, 1 square root of 2, 1 square root of 2. These are orthogonal vectors, which means if you have a cross product between first and second, you should get the third one. And therefore, you know, these are the Cartesian coordinate systems. Now, if I want to find A11, for example, I take the dot product A1 prime dot AE1, okay? Which means is 1, this is the first one, times 1 over square root of 2 plus 0 plus 0, correct? So this is how I calculate each term for the homework number 3, which is find transformation matrix, point A of your homework. Questions? Okay. So if you know the transformation, then you can apply this transformation to the vector, and here is vector xyz, but you can have fx, fy, fz, and find the coordinates of this vector in a different format. Okay. Ah. Interesting. So now I have I created a new okay. So any application of this AIJ or A alpha beta transformation matrix to particular quantity, then that would produce for me that value or this particular expression in a new coordinate system, in transform coordinate system. If I apply this to a scalar, then Aij has to be taken to the power of 0, which means it's 1, which means it is not applied, because the scalar in prime or unprime coordinate system is exactly the same value. For the vector, this is what we apply to the vector. So we can have this Aij is applied once, and therefore a vector is so-called tensor of first order, because this Aij is only once in the equation. We can do it for vector u or vector b, and then we can make a summation of transform by using the summation of tensorial term, or in other words, apply AIB to the summation of the vectors. If we are looking for higher order term, then we can, for second order, for example, we will need to do it twice. So like U alpha V beta altogether is a second order term, because we can have two free indices. Alpha is free because it's repeated only once, and beta is free also. And if we have alpha and beta free, then it means this is a matrix. If alpha and beta is 1, 2, and 3, then this would be U1, V1, first term, U1, V2, U1, V3. This is U2, V1, U2, V2, U2, V3, and a U3, V1, U3, V2, U3, V3. Okay? So basically, we know that if we have two indices, they are free. It means you can have a 3x3 matrix, and this which is, say, a tensor of order 2. And we know that this is of order 2 because if you have components of this tensor, which could be, this term would be W11, this term would be W12, this term would be W13, and so on, then transformation between unprime and prime, you need to apply twice as this mathematical equation is showing to us, okay? So if we want to do tensor order n, then we can expand this, and if this is the tensor from Q1 to Qn, which is n terms in the indices, and would like to capital T also n of them, but they will be P. So I will have to multiply A n times to produce transformation from unprime coordinate system to prime coordinate system. Okay? So if we want to get back to our vector, so V1 could be A11 V1 prime if we want to go from prime to unprime coordinate system, A21 V2 prime plus A31 V3, and V2 A12 V1 prime plus A22 V2 prime plus A23 V3 prime, and V3 is A13 V1 prime plus A23 V2 prime plus A33 V3 prime. So we can transform from unprime to prime or from in both directions, okay, using this transformation. Now, if we have vector V defined as we can see here, and we want to take a dot product, we remember that this is V1 square plus V2 square plus V3 square, correct?
Oh.
And the same, this is a scalar, correct? This is a scalar. So vector in unprime coordinate system, this is a number, scalar. So this must be the same as dot product between the same vector, but in different coordinate system. So we can say that this is also V1 prime square plus V2 prime square plus V3 prime square. Okay, that is true. So if we now take for the each term going the other way around, I hope that this PowerPoint with annotation will be saved, and then I will upload to Brightspace. So V1 prime dot V1 prime would be now taking A11 square plus A12 square plus A13 square V1 square plus A31 square plus a not 31, excuse me, A21 square plus A22 square plus A23 square V2 square, just by adding and grouping together A31 square plus A32 square plus A33 square V3 square plus 2 A11 A21 plus A12 A22 plus A13 A23 V1 2 square plus A31 no, this is 2 plus 2 again A11 A31 plus A13 A32 plus A13 A33 V1 V3 plus 2 times A21 A31 plus A22 A32 plus A23 A33 V2 V3. And since this is V1 square plus V2 square plus V3 square, then we can say that this bracket here must be equal to 1. This bracket here must be equal to 1. And this bracket here is equal to 1. And that 2 brackets, 3 brackets, this must be 0, this must be 0, and this must be 0. So in other words, the squares of the components of each row of this matrix is 1, and the mixed is 2. Okay? Since one of the homework problem is also asking for looking at the symmetric and anti-symmetric tensor, I put it together here so you can see how you can define from one tensor summation of 2 of them, which are shown here. But coming back to our definitions of the products between that I just said, that some of them is 1, some of them some 0, they are bringing to us so-called Kronecker delta. So if you expand this form here, which is alpha, gamma, beta, gamma, you can see that alpha is free and beta is free. However, gamma is the same. It is so-called dummy index. If you have a product of any matrices, any tensors, where you have indices which are repeated, dummy or repeated, it means it is summation. You have to do summation. If you have free, it means it is a matrix. So this would be a matrix, 3 by 3 matrix. However, each term of the matrix, like delta, alpha, beta, would be A alpha 1, A beta 1 plus A alpha 2, A beta 2 plus A alpha 3, A beta 3. I made a summation for gamma because gamma was dummy variable. So I had to apply summation. And if you have alpha and beta 1, so you have A11, A11, which is A11 square. And then you have A12 square and A13 square. And so this is the same term that we just defined here, which we said it is 1. So you can see that this Kronecker delta would be delta alpha beta is giving us all 6 terms. Some of them is 1, some of them is 0, and 1 would be for alpha and beta to be the same, which could be either 1 or 2 or 3. And if alpha is not the same, then this Kronecker delta is 0. And expansion is basically giving us those terms that I described on the board. Okay. So let's go back to that Kronecker delta. So you can see definition. Delta alpha beta is A alpha gamma, A beta gamma, and which you can expand by using the summation convention. Now, using the same summation convention, the Kronecker delta can be also used as summation, like delta gamma gamma or lambda lambda is nothing else than delta 1 1 plus delta 2 2 plus delta 3 3, because we have repeated index. So we have to apply summation. And since this is 1 and this is 1 and this is 1, so you make a summation of those 3 ones and you become 3. So delta lambda lambda is basically a number 3. But delta I lambda j lambda, it is basically delta I1 delta J1 plus delta I2 delta J2 plus delta I3 delta J3. So this is how you can expand each term in terms of a free index, and therefore you can reproduce this Kronecker delta in matrix form, because it is free, 2 indices, they are free of free. So it means they are expressing as parts of the matrix. This matrix is basically unit matrix, which has all the diagonal terms to be 1 and everything else is 0. So the Kronecker delta is very useful in using the expression or manipulation of tensors in our notation. But other terms, of course, also could be useful. For example, if I have Aij B JK, what is this? Well, I notice that you have one repeated matrix, so which means summation. So I will have AI1 B1 K plus AI2 B2K plus AI3 times B3K. Okay. But I and K are basically terms that need to be put in the matrix. So A1, if I is 1 and K is 1, so it would be R11 B11 plus A12 B21 plus A13 B31. This is the first term of this matrix. And so on. I will have to do the whole set of summations. This first term is I is 1, K is 1. this term will be I is 1, k is 2, I is 1, k is 3, and the next one here would be I is 2, k is 1. I is 1, 2, and k is also 2. So if you apply those ij to the summation that you just defined and on top, you can find all terms of this matrix. And this is the part that you want to do in the homework for the problem number 1. Okay, so I'm telling you how to do the homework. Okay. Now the second important tensor is going to be so-called alternative tensor. And this is the epsilon ijk. This is the alternative tensor, which is defined as 1 to be if ijk are in cyclic order, 1, 2, 3, or 1, basically moving 2, 1, 3, and so on. So 1, 2, 3, 3, 1, 2, 2, 3, 1 is 1. This is shown here. If you replace any of them and you repeat any of them, then it is 0. And if you permutate in the opposite direction, so instead of 1, 2, 3 is 3 to 1, then it is minus 1. Okay, so this alternative tensor could be, alternating tensor could be either 1, 0, or minus 1. And now this one is very important because we can use for creating cross product. So for example, if you want to have cross product to be generated using tensor algebra, you basically put epsilon ijk, aj, bk. So how that would work? Okay, you see that I is free vector, free index, I is free, and jk is repeated. So you have to make summation for j and k. So ci would be epsilon I 1k a1 bk plus epsilon I 2k a2 bk plus epsilon I 3k a3 bk. So as you can see, I first make summation for only one index, one dummy index, which was j. And now for each term, I can expand this to be summation for k. So this term would be epsilon I 1 and k also 1. So a1, b1, correct? But epsilon repeated is 0, so that will go away. Now, if k is 2 plus a1, b2, so I have a epsilon I 1, 2, and so on. And of course, I would be either 1 or 2 or 3. So if you expand everything, it will be very long terms, but many of them would be zeros. Some of them would be positive 1, some of them would be minus 1, and will regenerate the typical 3 terms for vector C, which is the cross product A cross B. Okay? So this is how you do operate using this alternative tensor. One way of remembering when it is positive 1 or negative 1, if you write on the paper 1, 2, 3 in the clockwise direction, then this would be producing the positive 1. So 1, 2, 3 is positive, 2, 3, 1 is positive, 3, 1, 2 is positive. But if you go the opposite orientation to this one, which means you go the counterclockwise, then you will produce minus 1. 1, 3, 2 is minus 1. 3, 2, 1 is minus 1. 2, 1, 3 is minus 1. Okay, so instead of remembering all of that, which is shown here, you can simply draw this small picture and you can generate the results of this particular values of the alternating tensor. Okay, any question? Okay, so now it's very important to know that if you have any term that you express like x alpha x beta multiplied by a alpha beta for alpha beta 1, 2, 3, then you will produce so-called homogeneous quadratic form of the equation, which again you have two dummy variables. So you can see that this would be a 1 beta x. It means I take alpha first, 1 x beta plus a 2 beta x2 x beta plus a 3 beta x3 x beta. Now I have to make a summation of the second term. I'll write it here below. So a11 x1 x1 plus a12 x1 x2 plus a13 x1 x3. All these three terms are coming from one term here. Okay, this is how you expand. Then you do the second one, which is a2 1 x2 x1 plus a31, excuse me, a22. Keep the two constant x2 x2 plus a23 x2 x3. These three terms are from the second term, and summation of the a31 x3 x1 plus a32 x3 x2 plus a33 x3 x3. So if you now you have x1 x1, that means this is x1 squared times this term. So all over you will get the quadratic so-called homogeneous quadratic form in terms of x1, x2. And those x1, x2 could be anything, any part of the matrix. So if you apply to stress or strain, you will get so-called, or the moment of inertia components, because moment of inertia is also second order tensor. You can produce so-called eigenvalue problem, which means you can find roots of this quadratic formulation, and those would be three roots, and those three roots are called principal values of this function x. For the stress, it would be principal stresses. For the strains, would be principal strains, and for the moment of inertia, would be principal moment of inertia. And each of the orientation for the eigenvalue or the principal value would be principal direction. So for example, for the if this is stress or strain, then for the principal or coordinate system that would be reproduced using eigenvalue problem, which basically is giving you that general formula, which is giving you 3 roots by taking the determinant of this bracket to be 0, and then you have R1, R2, R3, and plug it back to this matrix, and you will have 3 equations with 3 unknowns. In addition to the squares of the Aij, which are those direction cosines, will give you the fourth equation, because the first 3 are not independent. Only 2 of 3 are independent. And we will solve some of those problems later, and we'll be able to use that in to find the principal directions and principal stresses and principal strains and principal moments of inertia. The final tool that would be used is to express, to merge kind of linear algebra with tensor algebra. So for example, if you have a tensor A and B, and you know that A can be expressed as A small aij and B a small bij, then A plus B is basically this, well, assuming that this is n by m matrix, then you can have a summation of each component for that matrix. So if you want the so-called subtraction, then you do the same with the negative value of the second term. And if you want to have transform form, so Aij would be regular, and transfer A transpose would be Aji. So you basically switch the terms from one with another. And if you have multiplication of a scalar by a matrix, then you can have each term multiply or divided by that scalar to get the results. So the transformation of the matrix using the tensor algebra is very, very useful. Okay, so these are the different forms that are used in the like taking the B I alpha A alpha j. It is to take summation, okay, for alpha. So, but I and j will give you a 3 by 3 matrix. So you know the outcome of this is 3 by 3 matrix, but each term is calculated as a summation for using the dummy variable, which we already used here in some cases. So again, if you have an example, A capital A with index I and B, J, then this is the same as matrix with products of each term. If you have one dummy variable, you need to expand this dummy variable and substitute them for each term using this summation. Now, if you have a third order tensor and multiply with second order tensor, the outcome of this is the second order tensor. So the reduction of the order if you multiply the higher order tensor by smaller order tensor. Now, also in tensor notation, we can express the derivatives. So if you have the derivative of the I, j, k with respect to xn, we can express this I, j, k dot, comma, n. That comma is derivative. Okay, so we will remember that derivatives are also useful for us. Now, if we have the coordinates xj, and we know that are related to I prime, or x j prime is AJI xi, we can go in both directions. Then we can differentiate dx I prime dx n would be the same as a ji dxi dxn. So in other words, the derivative of the coordinates is first order tensor. So in other words, is also Kronecker delta. So this is the same as delta im, because derivative of this particular function with respect to the second or coordinate with respect to other coordinates, if this is the same, dx is 1, dx dy, if they are independent, is 0. So dx dz is also 0. So the derivative, the scalar function derivative is the first order tensor. If you take the gradient, which is the gradient of the scalar function, so delta phi is the same as phi comma j. Phi comma j or phi comma I is a vector. So the gradient of the function you can see is the derivative with respect to xi, which is x1, x2, x3. The gradient of a vector is vi comma I. So this is a scalar because nabla coefficient is a vector. So vector dot vector is a scalar. So therefore, you can see this would be v dv dx dv dy dv dz. So this is summation, basically dv1 dx1 plus dv2 dx2 plus dv3 dx3. This is what it means in the short notation. And again, if this is the biharmonic equation, would be with the derivatives would be comma I, which is the same as d square phi d x1 square plus d square phi d x2 square plus d square phi d x3 square. Okay, so all of them are kind of falling into one place for every term of this relationship. Now, if we go to the stress using the that's interesting. New slide. Okay, so if we take the so-called eigenvalue problem, so we have the stress ij aik ajl sigma kl dot kl, and we know how to calculate this aij is a prime dot aij. Okay, these are the coordinates of two unprime and prime coordinate system, and we have direction cosines. So the a practical way of the stress is, first of all, to take the stress which is given, sigma ij, take the Kronecker delta, and use this as the sigma head. These are the roots of the coordinate system. The determinant of this will give us sigma 1, sigma 2, and sigma 3. So this would be, in other words, the determinant of this formula will give you third order polynomial because you will have 3 roots. So for each, in practical way, would be to produce that determinant, which is taking the stresses and putting in the radial, this is 1, 3, this is 2, 3, 3, 1, 3, 2, sigma 3, 3 minus sigma. Okay, and if you express this and find the determinant, which means multiply this times this times this, you will get the equation of that form. Minus sigma 3 cube, excuse me, minus sigma cube plus sigma 1, 1 down plus sigma 2, 2 plus sigma 3, 3 sigma head square plus sigma 1, 1 sigma 2, 2 plus sigma 2, 3 sigma 3, 2 plus sigma 1, 2 sigma 2, 1 plus sigma 1, 3 sigma 3, 1 minus sigma 1, 1 sigma 3, 3. So this was minus here, and minus sigma 2, 2 sigma 3, 3 times sigma head, and plus sigma 1 sigma 2, so 1, 1 sigma 2, 2 sigma 3, 3 plus, and so on, combination of all of those terms from this determinant. This summation of the radial components 3, 3, 1, 1 to 2, 3, 3 is so-called first invariant. This is second invariant, and this is third invariant. So we can say that this equation basically is like sigma 1 cube minus I1 sigma head square plus I2 sigma head minus I3. As you can see, this is polynomial, third order polynomial. So you will get 3 terms which are principal stresses, sigma this is sigma head cube minus I1 sigma head square I2 and so on. I1, I2, I3 are invariants for any stress in any particular current system. They are always the same. And therefore, you will get sigma 1 head, sigma 2 head, sigma 3 head, which are principal stresses. So one of the homework will be to use this relationship for the solving the problem. Once we have the principal stresses, then we need to write the equation of that form. Let's see. Slide. So now we will put for sigma 1 hat, the equation would be like this: sigma 1 minus sigma 1 hat, which is known already. The rest of the stresses, they are copied from the original stresses. Sigma 2 minus sigma 1 hat, sigma 2 3, sigma 3 2, sigma 3 3 minus sigma 1 hat. Okay, and this you multiply by unknown unknown vector, and you say this must be 0 on the other side. So for example, first equation will be sigma 1 minus sigma 1 hat times E1 plus sigma 1 2 times E2 plus sigma 1 3 times E3 is 0. These are unknowns, E1, E2, and E3 in this equation are unknowns. The black are known. Second equation, sigma 2 1 E1 1, E1, not E1 1, simply 1. Plus sigma 2 2 minus sigma, which is given E2 plus sigma 2 3 times E3, okay, is equal to 0. Second equation, and theoretically you could use the third equation, but instead you better take those three equations, and three equations, three unknowns, you will get E1, E2, and E3, but they will be two of them because it's quadratic. So you will have E1, for example, and minus E1, and so on. So combination. So you need to make sure that you use Cartesian right-hand rule for that system. So E1 and 2, you have the freedom to pick, but E3 has to be right-handed rule. Or in other words, E1 cross E2 must be E3, which will eliminate one of the solutions. Any question? Okay. So I think I covered a lot of things for you. If you have no questions, I will suggest you to read what is in that chapter 1, and start working on your homework, as it is free. I mean, it is fresh in your mind, and hopefully everything will be perfect later for you once you solve all the problems from the homework. Okay, any questions?
Hi, Professor. Can you hear me?
Excuse me?
Can you hear me?
Yes?
I was wondering, for our exams, are they going to be at home, or are we going to have to come in person to take the exams?
No, they will be take home.
Okay, thank you.
So we will have number of homeworks. One of the homework will be called midterm, and one homework will be called final exam. Okay. So basically, there will be number of problems to solve. All of them would be at home. By elasticity, you have to solve a lot of problems. This is just like any other mathematics related or physics related course. A lot of problems solved, and then things starts to be useful for you. Okay. So of course, if you have questions regarding homework, do not hesitate to ask. I'm here to help. And I think that would be enough for today. We didn't make any break. So I think I can let you go. Okay?
Thank you.
Okay.
Dr. Binianda,
Yes.
if we have any questions while we are reviewing this material later on, can we email you in person, like individual emails? Is it okay for you?
Yes, absolutely. Send email
All right, thank you.
anytime. I'm working for you. Okay?